So welcome to lecture 2.8. This lecture is about steady state error and error constants. We have been talking about steady state error from the beginning of this topic, wherein we have talked about the time domain specifications of second order systems. But now we are going to technically see exactly what steady state error is. So the basic definition is here. The steady state error is the difference between the input and the output for a prescribed test input as time t tends to infinity. And the logic is that because the input is also the desired output, and I have discussed this in detail in my earlier lectures. So basically, when you are looking at this error, you're comparing the desired output with the output of your system, actual output of your system, and trying to look at that error as time t tends to infinity. And this is a very logical definition of steady state error. Now let us look at the manifestation of this definition on an open loop system and a closed loop system. So from this, in the first diagram, the error is simply going to be as a in the frequency domain, it is simply going to be Rs minus Cs, which is Rs minus Rs into Gs, which is going to be Rs 1 minus Gs, right? So, and from the final value theorem, which we have studied in Laplace transformation, from the final value theorem, we can very simply write that if you want to find the value of a function as time t tends to infinity, this can be written as the value of this function as s tends to 0 when you multiply the Laplace transform of the function with s. So using this final value theorem, which is a standard theorem in Laplace transformation, we can write down the steady state error E steady state or E infinity generally as limit s tends to 0 SRS 1 minus GS, right? So in case, for example, your GS for this open loop system is, say, for example, 1 upon S into S plus 5, then you can calculate E infinity to be equal to, and your, say, for example, your input RS is 1 by S, you can calculate E infinity to be limit S tends to 0 S into 1 by S into 1 minus 1 upon S plus 5, right? So this would actually be a large value because you have an S in the denominator, so E infinity would be infinity, right? But in case, say, for example, for the same system, this GS is 1 upon S plus 5, then your E infinity is going to be limit S tends to 0 S into 1 by S 1 minus 1 upon S plus 5. So you can substitute the 0 in this, and this is going to be E infinity is equal to 1 minus 1 by 5, which is 4 by 5. So the value of E infinity would change depending upon the transfer function, and it is explicitly dependent upon the number of zeros and the number of poles at S is equal to 0. So we'll look at this in more detail soon. Now let us look at the closed loop system here that we have. Now how would we calculate the steady state error in this? By this definition, we should also again do this limit S tends to 0 Rs minus Cs and multiply this with S. But we see here that we are not comparing the output directly with the input, right? We are multiplying the output with the transfer function of the transducer, and then we are comparing it with the input. So our steady state error would actually come here, and this is because the signal that is comparable to the input is actually the signal output multiplied with the transducer gain. So here there will be a slight change in the definition of the steady state error. So for the closed loop system, we'll have limit s tends to 0 s times, so you have to compare rs with cs into hs, right? That's the only difference, but actually the basic essence of the definition is the same. We are comparing the output and the input, but output has to be made compatible to the input. So in this case we are multiplying it with the transfer function because we are actually doing it in the application. Like for example, in the antenna azimuth position control system, there is an output potentiometer with whose gain you are multiplying the position and converting it into a voltage, so that you are able to compare the two voltages together, right? So let us now look at this and see whether we can simplify it. We already know that for this closed loop system, cs by rs is gs divided by 1 plus gs hs. So we can substitute this in here and see whether we can simplify this further. So E infinity is going to be limit s tends to 0 s rs minus, now let us substitute the value for cs in this. So we have gs 1 plus gs hs, this into rs into hs. This is when you substitute the definition of the transfer function relationship into the definition of the steady state error. So this gives E infinity is limit s tends to 0. Let us take out s rs outside and see what remains. So you have 1 minus g s hs divided by 1 plus gs hs, and we can further simplify this to give us the standard definition of the steady state error for closed loop system, which is given by srs divided by 1 plus gs hs, right? So this is the standard relationship for the steady state error for closed loop systems. Now if you look at this more closely, we see that GSHS is the open loop transfer function. Open loop transfer function for the closed loop system. And the so we can say that if a closed loop system has the open loop transfer function given by GSHS, then the steady state error of that system is going to be limit s tends to 0 srs divided by 1 plus gshs, right? So now let us look at the steady state error for different inputs, right? So if our rs is, for example, a unit impulse input, a unit step input, a ramp input, parabolic input, what is the steady state error going to be, right? So let us start with unit step, for example. So rs is 1 by s, rs is 1 by s square, rs is 1 by s cube. All right, and let us look at what is going to happen to the steady state error. So when we substitute 1 by s here in the original definition, we'll see that this s and 1 by s will cancel, and what you are left with is only limit s tends to 0 1 upon 1 plus gshs, right? And you can write this as limit as 1 upon 1 plus limit s tends to 0 gshs, right? Which you can write as 1 upon 1 plus kp. Kp is called the position error constant. Position error constant. In fact, it is called the static position error constant. And the definition of kp is simple. Limit s tends to 0. You multiply the open loop transfer function and put limit s tends to 0. Find the open loop transfer function and see the value of the open loop transfer function as s tends to 0. That is your position error constant. Now let us look at the steady state error when the input is a ramp input, right? 1 by s square. So when you do that, you'll see that you'll have 1 by s remaining in the numerator, and the denominator would be 1 divided by, so let me write this down. So this will be limit s tends to 0. So 1 by s remains in the numerator after I multiply it with s with rs, and in the denominator I get 1 plus gshs, right? So I can simplify this as 1 upon s plus s gs hs, and when I put this limit s tending to 0 in this, this s here would become 0, and I'll get 1 upon limit s tending to 0 s gs hs, which is 1 upon kv, the velocity error constant. So this is your static velocity error constant, which is given by limit s tending to 0 s gs hs, right? These are definitions which will be useful later on, we'll see. But what we are trying to derive is the value of the steady state error for a general closed loop system for different types of inputs, right? Now let us look at the third input, which is the parabolic input. And if we do the substitution again, the only difference that we'll have is we'll have in the denominator s square plus s square gs hs. So we can write down the error, steady state error, limit s tends to 0 s square gs hs inverse. So this is called 1 upon, this is 1 upon ka, where ka is the static acceleration error constant, and is given by limit s tends to 0 s square gs hs. So to briefly summarize, you have basically three types of test inputs, right? 1 by s, 1 by s square, 1 by s cube. These are your three test inputs, and your steady state error, which you have defined as this, derived as this. Your steady state error for these test inputs is going to be 1 upon 1 plus kp, 1 upon kv, and 1 upon ka, where kp, kv, and ka are static error constants, and their definitions are given here. Kp is 1 limit s tends to 0 gshs, kv is limit s tends to 0 s gshs, and ka is limit s tends to 0 s square gshs. Now, why is this important? This is important because this is going to tell us something about different types of systems for different values of the open loop transfer function gshs. Let us assume that our gshs can be written in this form: 1 plus s t tau 1 plus 1 plus s tau 2, 1 plus s tau 3, so on and so forth. It goes up to some number, right? And in the denominator, you are able to write it like this: 1 plus s tau a, 1 plus s tau b, and so we are not restricting the order of the system. So suppose you're able to write your open loop transfer function like this, and you're able to actually separate the poles of the open loop transfer function which are at s is equal to 0. Now you see, this is going to be very important in determining your error constants, like, because your position error constant is limit s tends to 0 gshs. So for a system of m, for a system whose value of m is equal to, let us look at the values of m, right? 0, that means m is 0, m is 1, m is 2, For these values of m, what are the values of my static error constants? What are the values of my kp? What is the value of kv? What is the value of ka? So you see, when m is equal to 0, that means limit s tends to 0 gshs, you have to put in all the values of all these values equal to 0. You'll see that the value of kp, let me do this here. So this is kp is equal to limit s tends to 0. Now your this is 1 plus s tau 1 divided by 1 plus s tau a, and these continue since your m is 0. So once you do this, you see that the value of kp is equal to the value of the gain for m is equal to 0, right? Now for the same system, if m is equal to 1, that means you have an s here. You have an s here, so the value of kp is going to be infinity, because this s is tending to 0, and for m is equal to 2, the value of k is going to be infinity. Now for the same system, if we are trying to find out the velocity error constant, then what we need to do is to just multiply this gsh. So kv is limit s tends to 0 s gshs. Now for m is equal to 0, gshs would be limit s tends to 0. We have s in the numerator, and gshs is k times 1 plus s tau 1 plus s tau m. And let me put s is equal to 0. You'll see that everything is multiplied with this 0 here, right? So kv is going to be 0 for a system whose m is 0, right? And if m is 1, for example, then you have an s here in the denominator, because the value of m is 1. So you have a pole at s is equal to 0, and this s and this s will cancel out, and you will get k as the value of the velocity error constant. And if m is 2, then you still have one s left in the denominator, because you'll have an s square here. So one s would cancel and the other would remain, and you'll get an infinity here. In a similar way, for the acceleration error constant, you get 0 and 0 here, and k here, right? Because your acceleration error constant is defined as limit s tending to 0 s square gshs. So it is limit s tends to 0. Now you see s square you multiply with k 1 plus s tau 1 and divided by 1 plus s tau a, so on and so forth. Since there is no s there, it's a m is equal to 0 system, so s to the power 0 here in the denominator. And when you put s equal to 0 here, everything gets multiplied by 0, you get a 0. And even if you have one s term here, that s and this square will cancel, you'll still get a 0, because there is an s in the numerator. And if you have s square here only, then this s square and s square will cancel, you'll get a k. So these poles of the open loop transfer function at s is equal to 0 determine the values of the static error constants, and consequently they also determine the values of the steady state error. This is called the system type. So this is a type 0 system if its open loop transfer function does not have any pole at s is equal to 0. It's a type 1 system if its open loop transfer function has one pole at s is equal to 0. It's a type 2 system if its open loop transfer function has two poles at s is equal to 0. And if it's a type 0 system, its position error constant is k, its velocity error constant is 0, its acceleration error constant is 0. If it's a type 1 system, its position error constant is infinity, its velocity error constant is k, and its acceleration error constant is 0, so on and so forth. So now we can combine the information that we have in this table and this table to see what are the steady state errors, right, for the different systems, for the different system types. So for rs equal to 1 by s, which is unit step, 1 by s square, which is ramp, and 1 by s cube, which is parabolic. And let us look at now the three types of systems that we have seen: type 0, type 1, type 2, depending upon the number of poles or the value of m. So we have already seen that the steady state error to step input here is 1 upon 1 plus kp. So the steady state error is in general equal to 1 upon 1 plus kp for step input. So now what we have to do is to substitute the values of kp for type 0, type 1 and type 2 systems. So the value of kp for type 0 system is k, so the steady state error is 1 upon 1 plus k. The steady the value of so this is type 0 system, right? So the value of steady state error for type 0 system, type 0 system the value of the velocity error constant is 0. Okay, now let us so we have substituted this. Let us now look at the step the value of the position error, the value of kp, for a type 1 system. So the value of kp for a type 1 system is infinity. That means this is going to be 1 plus infinity, so this error is going to be 0. And similarly, the value of the position error constant for a type 2 system is also infinity, so this is again going to be in 0. So what this means is that if you apply a step input to a type 0 system, a system which does not have any pole of the open loop transfer function at s is equal to 0, then there would be a steady state error, right? And there would be no steady state error if the system has one pole or more than one poles at s is equal to 0, the open loop transfer function of the system. In a similar way, let us look at the ramp input. For the ramp input, we know that the steady state error in general is the reciprocal of the velocity error constant. So this is 1 by kv, the steady state error for the ramp input. Now what is kv for a type 0 system? Now we have to look at this column. For a type 0 system, kv is 0. That means the steady state error is going to be 1 by 0, which is infinity. What is the velocity error constant for a type 1 system? The velocity error constant is equal to k. So that means for a type 1 system, it is 1 by kv, which is 1 by k. What is the steady state error for what is the velocity error constant for a type 2 system? The velocity error constant for a type 2 system is infinity. So the steady state error is 1 by velocity error constant, which is 1 by infinity, which is 0. In a similar way, we can find the steady state error to the parabolic input, because the steady state error to the parabolic input is 1 by ka, the acceleration error constant. We have already seen that here in this table. So the steady state error for a type 0 system is going to be 1 by 0. For a type 1 system, again 1 by 0, which is infinity, and for a type 2 system, it's going to be 1 by k. So we can write down infinity because the acceleration error is 0, and the steady state error is the reciprocal of the acceleration error constant, infinity and 1 by k. What we can see from this table is that the steady state behavior of the system, right, the steady state behavior of the system as the system type increases is improves. So as you move in this direction, that is you are adding poles to the open loop transfer function. You are adding poles to the open loop transfer function at s is equal to 0. You see that the performance of the system with reference to the steady state error improves. You are going in the direction of decreasing steady state error. This is one thing that we notice. The other thing that we notice is that as we increase the complexity of the input, as we move from step to ramp to parabolic, there is deterioration for different for all system types. There is deterioration in the performance of the system. It is more difficult for a system to have zero steady state error for a ramp input as compared to step input. We can see that the steady state error for the step input of a type 0 system was a constant, but it became for the type 0 system, the steady state error became infinity as you moved on from step to ramp. For a type 1 system, the steady state error for a step input was 0, but as you kind of made the input more complex by making it ramp, or you increase the demand on the system, because you're asking now your system to actually match the input, which is constantly changing with time, your steady state performance is deteriorating, right?